we're going to get started here looking at first chapter 5. You should be able to show how carbon hybridizes to sp2. We have two carbons here that are connected by one bond which represents the sigma bond, but the other one represents a pi bond. Well, let's recall that pi bonds are made from what? That's right, unhybridized p orbitals. Carbon in the ground state. So what we have is 2s, 2p. 2 electrons here, 1 electron here and here. We don't have the proper setup to be able to bond 1, 2, 3 atoms to each of the carbons. So what we're going to do is we're going to allow one of those electrons to get promoted up to the p orbital from the s orbital. We're going to now draw a carbon excited state, 1 electron in each of the orbitals. We can bond to 3 atoms. We still have 1 left over, unhybridized, for the pi bond. But we have to recall that the p orbitals are 90 degrees to one another, so therefore we want to hybridize these, and we're going to grab the s orbital, 2 of the p orbitals, 3 atomic orbitals. We should generate 3 hybrid orbitals, 3 new orbitals. We're going to call those sp2. And recall that the angle up there close to 120 degrees. Know how to name simple alkenes. So what we're going to do is we're going to number these. Remember, we want the double bond closest to the side where the double bond starts. So that is going to be from the right side. 7 total carbons here. The double bond starts at carbon number 3. 3, and the prefix for 7 is kept. And then because we have a carbon-carbon double bond, our root is En. Because this is a hydrocarbon, remember, the ending is E. So now we have substituent, which is a methyl group. This is a ring, so cyclo, a 5-membered ring, pent, En, E. Know when to use cis and trans or E and Z. What we said that we'd use if the alkene has the same groups on either side like this, trans to butene. Trans again because the CH3 here and the CH3 here are opposite sides from one another, and are also on the molecule are 2 hydrogens, and these kind of help us see that our 2 methyl groups are trans from one another. What happens if we have a double bond that now has like a Br over here, and we'll put an H over here? Now what we have to do is we have to look at the priorities of these groups. On the left-hand side of the molecule, who gets the higher priority? Well, since Br has a higher atomic number, this gets higher priority. And over here, the methyl group gets higher priority. So what we have here is these 2 high priority groups are on the same side of the molecule. So we're going to start this out by saying they're on the same side. So we're going to say this is a Z 2 bromo 2 butene. Okay, so that gives you an idea between when to use E and Z and when to use cis and trans. How can we tell if an alkene is more or less stable? Now, I'm going to draw 2 alkenes here. First compound, 1 butene. Second compound is 2 butene. Now let's see how many hydrogens there are directly attached to the double bond. In 1 butene, I have 1 hydrogen here, 2 hydrogens over here. As opposed to 2 butene, where I only have 1 hydrogen on either side of the double bond. This one will be more stable because it has the fewest number of hydrogens directly attached to the double bond. We call that Zaitsev's rule. We call it the Zaitsev product because it has the most highly substituted double bond. The way to get 2 alkenes is by E1 or E2. Remember, we're talking about E1, tertiary haloalkanes. So we have this compound, methylcyclopentene, we're going to react it with hydrogen on platinum or palladium or nickel. And this type of reaction is called what? A reduction using hydrogen or hydrogenation. Realize that we're going to have both hydrogens come in on the same side. This is known as a syn addition of the two hydrogens. Now, if I add a haloacid like HCl or HBr or HI, this says here that it's a Markovnikov addition. It means that I should get the Br at the more highly substituted carbon, the hydrogen on the other side. So here's the Br, and here is my H. HBr peroxide is an example of anti-Markovnikov. Anti because we should get the Br not on the more highly substituted carbon, but on the other carbon. The Br on this side and the H over here. Hydration of the double bond, this should produce an alcohol, and again this is a Markovnikov addition at the more highly substituted carbon. In this case I'm getting an OH and the H over here again. X2 turns out to be an anti-addition of the two Brs. Unlike our hydrogenation, it was a syn addition. When I draw the Brs in, I should get them on opposite sides from one another. This is anti-addition of Br2 across the double bond. Osmium tetroxide, on the other hand, is going to give us a syn addition of two OHs. Both these OHs should be on the what? Same side, right? KMnO4, if I have heat here, instead of doing it cold, if this is heat, what it's going to do is cut the double bond in half, but since KMnO4 is such a strong oxidizing agent, I'm going to have a double bond on both sides. Here is my CH3. Now 2 carbonyls, because KMnO4 is such a strong oxidizing agent, this side that started out having just an H will wind up as the acid. Kind of similar to our ozonolysis product down here, we again get 2 Cl bond O's, but ozonolysis isn't as strong an oxidizing condition, so instead of getting acid, ozonolysis will stop at the aldehyde on the right hand side. And our last one here, which says X2 in water, because there's water in here, instead of getting the two Brs anti to one another, we're going to get a Br and an OH. The intermediate bromonium ion can form either up or down, so we're just drawing one of 2 possible products here. Wherever you put, let's say the Br, the OH has to be on the opposite side, because this is an anti-type addition. Using reactions, describe the difference between Markovnikov and anti-Markovnikov addition to an alkene. To draw your methylcyclopentene, and then literally draw one of 2 reaction conditions. The first one would just be regular HBr, but the other one is going to be HBr in the presence of peroxide. The bottom one is going to be the anti-Markovnikov, and the top one should be the Markovnikov. Now, I want you to realize that the top reaction is an ionic mechanism, where the bottom one is a free radical mechanism. Each reaction should go through the most stable intermediate. The top reaction will produce, there's no designation with stereochemistry here, so these things could be up or down. The Br should end up here, and this is my CH3, and my H over here. And the other one should give me the Br on the other side.